Mr. Taru, in this algebra lesson, we are going to continue our development of learning how to solve linear equations. I'm going to have links down in the description of this video in case you missed them. And I also have videos in order that I teach them in playlists, which you can find on the homepage of my channel or ProfRobBob.com. And we've been working through one-step equations, two-step equations, multi-step equations. In all three of those lessons where we're solving these linear equations, all the variables were on one side of the equation, either all on the left or all on the right. Well, now we're going to be solving equations with variables on both sides of the equation. And thus we're just continually adding more and more steps to our recommended sequence of steps that we want to follow to solve these linear equations. And the recommended steps, I believe that for the vast majority of the problems, if you walk through these mathematical steps in this order, that's the easiest way to get to the final answer, or the final goal, which is to isolate that variable, and so that you see, whatever it's equal to on the other side. But it's, you don't have to follow the sequence exactly, and sometimes it's actually more convenient to not follow the sequence. It's just a recommended list. Now, this lesson is going to have 5 examples. We're going to have 3 algebraic, just like this one, where there's here's an equation and solve it. The third one is going to be involving fractions. And the last 2 examples are going to be involving word problems. We're also going to discuss sometimes when you're solving these equations where the variables are on both sides, and this does not have to be the only case where that happens, but you're trying to isolate a variable, solve for a variable, and all of a sudden it just disappears. So what happens, or how will you recognize when an equation has no solution or an infinite number of solutions? Okay, and you're going to find timestamps to all of those examples in the description of this video as well. So if it gets a little long, or if I'm doing an example that's too easy, just go to the description and skip on to the next example. So we're going to distribute to remove parentheses. That's a multiplication step. We're going to combine like terms. Now when I'm talking about combining like terms, I'm talking about terms that are all on the left side of the equal sign or all on the right. And we're just going to add or subtract those together, whatever the signs tell us. Let's not forget that like terms terms are separated by addition and subtraction, and like terms are terms that have the same, they can be constants, or they have the same variables in those terms and the same number of those variables. In other words, look at those exponents, 2x and 3x squared. 2x has got 1x and 3x squared has got 2 of those x's. While I said x in both of those terms, they would not be like terms because, 3x, I'm going to get messed up what I said, but one of those terms only had 1x and one of those terms had 2. So you need the like or equal variables, the same variables, and the same exponent on those variables. But we're only dealing with linear functions here, so all of our exponents are going to be 1. We're going to add or subtract to move all the terms with the variable you are solving for to the same side of the equation. Now I kind of put that sort of in general terms. These are going to be one variable linear functions ultimately, and thus just move all the terms with the variable in it to one side of the equation. You can't solve for a variable, you can't isolate a variable when there's one on both sides. So an addition or subtraction will get those all together. We're going to add or subtract then away from the variable. We're kind of getting down to where we're probably going to be reviewing those 2-step equations. We're going to add or subtract away from the variable. And our last step, recommended step, is to multiply or divide away from the variable, and by then you should have that variable isolated, thus solve for. And then it's always a good idea to plug that number back into the original problem and check it to make sure it actually makes the 2 sides of the equation equal. So here we have our first example. It's 7m minus 5 is equal to 2m plus 15. The equal sign, or later when we solve inequalities, it's that equal sign or inequality sign that breaks the left-hand side of the equation up with the right. And we don't have any parentheses, so we're not going to have to work on the distributive property. Excuse me. We're going to combine like terms. Now, when I look at this equation, yes, there is a 7m and there is a 2m. These are like terms, but they're not on the same side. This example here, combining like, or the step here, combining like terms, I'm talking about, look at the, let's go left to right. Look at the left-hand side of the equation. to the left of the equal sign. This has an m and this does not. That's a constant. So there are no like terms on the left side of this equation. Now when you look on the right side, same thing. 2m and plus 15, this has a variable, this does not. Those are not like terms. So yes, 7m and 2m are like terms, 5 and 15 are like terms, but those are on different sides of the equation, so that's not what I'm referring to again in step 2. Add or subtract to move all terms with a variable you are solving for to the same side. Okay, but there's two thoughts you can have here when you're trying to get your variables, move all your variables to the same side of the equation. Some students, and actually I prefer this as well, they'll find the term with the lowest coefficient, and negative numbers of course are always going to be less than positive coefficients as well. They look for the smallest coefficient of your variable and they move that over with again addition or subtraction. They do that because they're trying to avoid creating an unnecessary negative value. Well then some students will get confused when the variable is not on the left hand side. I have a lot of students, I can give them even quite difficult linear functions, or any equation for that matter, where the variable's on the left and they get used to moving all of those constants and coefficients over to the right side of the equation, and they get that habit of, okay, everything's going to go to the right. And that's good when the variable is on the left. But when the variable's on the right-hand side of the equation, sometimes they get a little bit mixed up. So you really need to practice solving equations with variables both on the left and the right-hand side of the equation. But also you need to work on making sure that your final answer is right. So in this case, we're going to take the 2m on the right-hand side of the equation. It's a positive 2m, and because it's it's a single standalone term, it is positive. We're going to subtract both sides by 2m, and in doing this, we're going to move this 2m over with subtraction, and not only are we going to keep our variable on the left, which I see a lot of students, not all, but some students are more comfortable with, we're going to get that positive coefficient, so we're not going to create any unnecessary negatives. So 7 minus 2 is 5m minus 5, bringing down the equal sign straight down, we've got 15. And just do one step at a time, please, when you're solving equations. That can lead to a lot of small, careless mistakes as well with students that I see all the time. And actually, I'm kind of prone to doing that as well. Do one step at a time. Be very, very neat with your work. It's going to help you get the right answer when you're done. And please show all the steps for your teacher and for yourself. If you find this to be a really easy problem, and why am I talking so much through it? Maybe you already know what the answer is. The algebraic steps that we're following to solve these problems, you want to get these steps memorized. You want to get the foundation, the mathematical foundation, the logical foundation down on the easy problems, so that when you get to the more difficult ones, that maybe you can't do multiple steps in your head all at once. You'll have the required steps sort of ingrained into your thinking process to allow you to solve those more easily. So our variable is on the left-hand side of the equation. We have a multiplication of 5 with it and a subtraction of 5, or a negative 5. We want to undo that subtraction of 5 that's over here on the left-hand side with the variable we're trying to solve for by doing the inverse math operation. So just like we saw that positive 2m and we subtracted both sides by 2m, I'm going to see this negative 5 or the subtraction of 5, and I'm going to add 5 to both sides. The subtraction property of equality and the addition property of equality. And now we have 5m is equal to 20. Our last step here, let's see, is to, we just added or subtracted away from the variable. We added 5 to both sides. And now we're going to multiply or divide away from the variable. We're going to see that we have a multiplication of 5, so we're going to do the inverse math operation of multiplication, which is division. And remember, you can pretty much do anything you want to an equation as long as you do it once to each side, and that's the division property, or actually, multiplying by a fraction. Multiplication and division are really kind of the same. I can multiply by 1/2 or divide by 2, and that's really effectively going to give me this, the same result. And our final answer, we believe, is m is equal to 4. Well, that's only the answer if it can be plugged back into the original problem and the two sides are equal. That's what a solution is. You're also going to learn when you start dealing with two variable equations or equations of parabolas and lines and all kinds of good stuff, that a solution is also an x-intercept. It's where the graph crosses the x-axis. But here, we're going to take this value of 4 and we're going to plug it back into the original problem, do a check here, and we have 7 times 4, which is what I believe our solution is, minus 5, is equal to 2 times 4 plus 15. We have 7 times 4 is 28, minus 5. 2 times 4 is 8. Plus 15, we got 28 minus 5 is 23, and we have 8 plus 15, which is 23 as well, and there you go, bam! Number 4, or the value of 4, is the solution. It does make both sides of this equation equal. Let's get on to our next example. Alrighty, for example B, or the second example, we have x minus 9 is equal to 7 minus 2 plus x. So we can see with this particular problem, we do have a set of parentheses. And to get rid of those, so we can write it without parentheses, we're going to distribute through those parentheses. Distribute what? Multiply what through those parentheses? I picked this particular problem purposely for the fact that a lot of students, like if the equation was x minus 9 is equal to 7 parentheses 2 plus x, then you would correctly want to take the 7 and multiply it through those parentheses and write 14 plus 7x. But there is not, or it is not 7 parentheses 2 plus x, which would indicate 7 times the quantity of 2 plus x, or 7 times the sum of 2 plus x. There's a minus sign there. Okay, so a lot of students will incorrectly multiply still that 7 through the parentheses. But what you're supposed to multiply through a set of parentheses is, well, if there's a number there, is what is in front. Let me make a little bit more room and write in that implied value or coefficient of -1. And indeed, some students find it very helpful to write a coefficient in front of all of the variables when there's not one there, because there is an assumed coefficient or multiple of 1 in front of these variables. And now, if you give yourself that little visual reminder that it's not 7 times that quantity, it's 7 minus -1 times the quantity of, or the sum of 2 plus x. And that, hopefully, will remind you, as well as me verbally trying to teach you, that you're going to take -1 and multiply it through there. And now we've got x, or 1x, minus 9. No reason to write that 1 unless you just like it there. 7, -1, plus, notice I stopped writing, by the way, until I complete the multiplication. I'm not going to write an automatic plus or minus. -1 times 2 is -2. Now, I don't like to write plus negative. By the way, some students, when they first get into like an early algebra class, might be a little bit confused as to, is something a minus sign or a negative sign? And there is a different key on your calculator. But if I cover all that up and I say read what you're looking at, you would say -7. Now -2. Now if I uncover the 7, you would read 7 minus 2, and it's equivalently, it is really basically the same thing. You can write 7 plus -2 if you like, but I'm going to write 7 minus 2, and in that case just sort of think of a negative and a minus sign as the same thing. Then we have -1 times +1. Well, -1 times +1 is -1, and let's carry that x along with there because, well, there is 1. And now we have x minus 9 is equal to 7 minus 2 minus x. We just got rid of the parentheses going through the distributive property. Combine like terms. And again, I'm talking about like terms. I'm talking about terms that can be combined that are on the same side of the equation. On the left side, we have an x and a 9, a variable, a constant, a term with a variable in it, and a term which is simply a constant. Those are not like terms. On the right-hand side, we do have a couple of like terms we can combine. We've got a +7 and a -2, and so we're going to put those together, and we're going to get x minus 9 is equal to 7 minus 2, which is 5, minus x, or just simply 1x. Now we're down into step 3, add or subtract, to move all terms with the variable you are trying to solve for to the same side of the equation. Well, I've got an x on the left and an x on the right. So like the last one, I'm going to avoid creating any unnecessary negative coefficients. So I see that I have a negative 1x here on the right-hand side, and I'm going to undo that subtraction basically of x we have on the right by doing the inverse math operation, which is adding 1x. So the 1x and the 1x are going to be 2x minus 9 is equal to 5. And now we're getting into reviewing those two-step equations. We're going to do the inverse math operation to move the 9 over to the right. And if you haven't been watching all of my lessons, the reason why I don't want to try and get rid of the 2, the coefficient of 2 that's in front of the x, that 2 is attached with or combined with the x through the math operation of multiplication. So I can divide everything by 2, and that would be a mathematically correct step, but look what's going to happen. 2 divided by 2 is 1. 9 divided by 2 is, well, 9 divided by 2. It comes out to either a decimal or you need to leave it as a fraction, and that's just going to unnecessarily complicate the problem. Dividing by 2, at least with the 9 and the 5, would give you a decimal that ends immediately, 0.5, but say if you have a run-on decimal or a very long decimal that you have to deal with through the rest of the problem, there's no reason to do that to yourself. Let's just add the 9 away from the x first. Do my recommended step 4, add or subtract away from the variable. The variable's on the left, so we're moving everything to the right. We get 9 minus 9, which is 0. We get 2x is equal to 14. We're going to undo, with the x still, we have a multiplication of 2. We're going to undo that value of 2. And we're going to get x is equal to 7. And that is the solution. Now, it's always a good idea to check your answer, but to just sort of making sure that this lesson doesn't run too long, I'm going to step out, show you the check to make sure that 7 is the solution, and come back with our third example. Third example that deals with fractions. Bang! Example C, third example. We got 2/3 plus 1/2, or 2/3 h plus 1/2 times the difference of h minus h and 8 equals 7/6h plus 3. Okay, so what do? We have parentheses. We're going to distribute through those parentheses to rewrite the sentence, open sentence, the equation, so that it does not have parentheses. And that means that we're going to have 2/3 h plus 1/2 h, because 1/2 times 1 is 1/2, and then positive 1/2 times negative 8, well, 1/2 times negative 8. When you're working with fractions, you should have those numerators and denominators all line up, or basically just have everything look like a fraction, and you go straight across. So or you can reduce before you multiply. I think for this one, I'm going to multiply straight across first. We have 1 times negative 8 is negative 8, and 2 times 1 is 2. And we're going to reduce that fraction. Both the numerator and denominator have a common factor of 2, or we can just divide by 2. And we get negative 8 divided by 2 is negative 4. And that is equal to 7/6h plus 3. Excellent. Now we are going to look to see if we have any like terms. Do we have any like terms that are on the same side of the equation that we can combine? So here is the equal sign separating the left and the right-hand side of the equations. There are no like terms on the right-hand side that has an h, and this term does not. It's just a constant. But on the left-hand side, we do have a couple of terms that will go together. We have 2/3 h and a positive 1/2 h. So these two like terms are going to come together, and the rest of our equation is going to be negative 4 is equal to 7/6h plus 3. And hopefully you're good at adding fractions, but just in case, we have 2/3 plus 1/2. Now you cannot combine fractions unless you have a common denominator, and our denominators are 3 and 2. Multiples of 3 are 3, 6, 9, 12, and so on. Multiples of 2 are 2, 4, 6, 8, and so on. Oh, yes, okay, we do have our lowest common multiple. There's other common multiples, but a common denominator, for convenience sake, you should have it be the lowest common multiple. So we need to take the 3 and multiply it by 2. So we're going to multiply the numerator and denominator by 2. And in case you don't know or forgot, the reason why we have to multiply the numerator and denominator by the same value is because 2 divided by 2 is 1. And 1 is the multiplicative identity. In other words, we're going to multiply this 2/3 by 1. It's still going to be 2/3. It's just going to look different, or equivalent to 2/3, equal to 2/3. But it's going to look different because we're multiplying it by 1 in a form of 2 over 2. We're going to need to take that denominator of 2 and multiply it by 3 to get it to match that lowest common multiple. And when we do that, so we're going to have 2 times 2 is 4, and 2 times 3 is 6, plus 3 over 6. And of course, once we have those common denominators, we don't add them. We're done working with the denominator. We're going to add the numerators. The values on top, and 4 plus 3 is equal to 7. Excellent. So 2/3 h plus 1/2 h is equal to 7 over 6 h. Lovely. So we've distributed to get rid of parentheses. We have combined like terms that are on the same side of the equation. And now we are going to try and get the variables on the same side. We have a variable we have h on the left and on the right. You cannot solve for a variable when it's on both sides of the equation. So we're going to pick one to move. Okay, so this is a positive value of 7 over 6h, or you could almost think of it as, an addition of 7 over 6h on the right-hand side. And actually, we kind of have the same thing on the left. So let's subtract 7 over 6h to both sides of the equation. This answer is going to be 0. Any number subtracted by itself, or anytime you add opposite numbers, you're going to get a value of 0. So this is going to be 3 equals, we have a 4 coming down, and well, 7 over 6 minus 7 over 6 is 0. Or we have like denominators, so 7 minus 7 is 0. Maybe you want to write this. And then you're like, okay, well, then it's h minus 4 is equal to 3. And then they come up with some kind of answer, and it's like, you're wrong. No. It is, sometimes you have this sort of weird thing happen where you're trying to solve for a variable and it just goes away. 0 over 6, 0 over a number is not an undefined value. That's probably not a bad thing to review either. Even my pre-calculus students annoyingly get this messed up at the beginning of the year. What is 0 over 5 and 5 over 0? Just to pick different numbers than what's over here. 0 over anything is 0, but you cannot divide by 0. That is unallowed. It is undefined. And when I say the answer is undefined, I mean it doesn't exist. It's not allowed. It's not even like in the realm of possibility. But 0 in the numerator always comes out to be an answer of 0. So if you're trying to solve one of these problems and all of a sudden all your variables go away, yes, that does happen. Don't leave it 0 over 6 for your teacher. They're going to realize that maybe you don't understand what that means. Don't write just h because you think it's weird that your variable is going away, because if you say the answer is h, then you're saying 7 minus 7 is 1, and it's not. 7 over 6 minus 7 over 6 is equal to 0, so the variable really just goes away. And you're left with the false statement. What does that mean? Well, I'll tell you what it means. It means that if the variable you're solving for is eliminated and the remaining closed sentence, a sentence that does not have any variables left in it, is false, then there is no solution. So, no matter what I plug in for h, because ultimately h just cancels out of the equation, we're going to get a false statement. This is no solution. All right, and if the remaining closed sentence is true, then there are an infinite number of solutions, because the variable, again, on both sides of the equation is canceling out, and it doesn't. But if it had said 3 is equal to 3, if that were a true statement, and that variable of h cancels itself out again, it doesn't matter what I plug in for h, it would have been true. It would have been an infinite number of solutions because I could put in an infinite number of values and still get a true statement. If, again, it had been true, like 3 equals 3, but since it's negative 4 is equal to 3, which is clearly incorrect, false, there is no solution. And by the way, if the variable cancels out and your closed sentence is true, what that states is the original equation is an identity, and a sentence that is always true regardless of what value is plugged in for the variable. Now let's get on to our 2 word problems. A widget company has a daily expense of $1,500, and each item they make costs them $1.45 to make. If they sell each widget for $3, how many, I don't know what kind of bad accent that is, but you know, how many widgets must they sell a day to break even? Okay, well, we got something in here about expense. And then we've got something in here about, you know, selling an item and sort of making some money. So we actually here have 2 equations. And there's a couple of ways to set this up, but I want to identify this as 2 separate equations. Let's talk about the expense. How much is it costing this company to run every day? Well, every day, an expense. A widget company has a daily expense of $1,500, and each item they make is costing them, each item that they are making costs them $1.45. And now I'm using the same color for a different part of the question, so I really meant to keep all that in blue, if you can tell the difference between the blue and the purple, I hope so. So talking about the expense, relating the expense of running the company to making items, each of which has a cost to make of $1.45. So we're comparing the number of widgets, and the reason why we're comparing the number of widgets to, well, the other thing we're comparing it to is expense and number of widgets. And we're talking about that because we have a cost dealing with something per day and that cost to make each one of those widgets. So we have our cost is going to be, let's see here, I was about to write the equation, but a discussion about independent and dependent, domain and range, explanatory and response. And going back to that label of independent and dependent variable, you have an expense, you're making widgets. What is helping to determine, you know, one variable over the other? It seems like as a company you would have some control over how many widgets you are making per day, and that value, the number of those widgets you're going to make, is going to help explain, besides the daily cost, explain how much your expense is to run the company. So the independent variable, therefore, would be the number of widgets, and the dependent variable would be the expense, or the domain is going to be the number of widgets, and the range, same different word, same type of idea, the answer, the range, is going to be the expense. So our cost, based on a number of widgets, is going to be that $1,500 per day, and that's just a one-time fee. Maybe it's a combination of your employees, your insurance, your electrical cost, renting the building, you know, whatever is making up the expense of your company, plus that maybe the materials it takes to make each one of those widgets, which is $1.45 times, and that $1.45 is going to, every time you make a new product, a new widget, it's another $1.45, another $1.45, another $1.45, and when you do that repeated addition, that cost, that new additional cost for every widget, repeated addition, is showing up as multiplication. So we have $1.45 again times the number of widgets. And I like writing my equations, especially in early algebra, using words, even though widgets is just kind of like a generic, you know, maybe I'm making watches, I'm making earrings, I'm making something, you know, a widget is just sort of a generic word for something that's being made. at least it's in words, and you can see that the final answer is going to be the cost for all of this production. Well, now we're going to be making money. You know, you're selling this stuff. We're not making products. No one makes products to just give them away. I mean, I know there are giveaways, but that is to drum up more business to ultimately make it back and increase sales of something else maybe. So they're selling this product at $3 a piece, and they're trying to create an income. So what they, let's see here, let's call it income. Their income is going to be, again, based on the number of widgets these people are that we're selling, and we're doing that for $3 a piece. Every additional item we sell is another $3 coming in, and 3 plus 3 plus 3 for every one that we sell. That's going to show up as $3, again, times, because repeated addition can be sort of shorthanded into multiplication, a notation of multiplication. We have our income is 300 widgets. Now, when you talk about revenue or income, there's a gross income and a net income, or gross revenue and net revenue, whatever language you might be using. When you sell something for $3, you didn't really make $3 in profit. That's called your gross income. The net income is saying, okay, well, I sold something for $3, but there was a cost behind that. If I only sell one item, then while I may have brought in $3, I've actually spent $1,501.45 to create that one widget. So I don't want to sell one widget and just bring in $3 because I've lost a lot of money that day. So how many would I have to sell just to break even? What would my sort of gross income, my gross revenue need to be so that my net income is equal to 0? You know, when would this break-even point occur? And then if we were solving inequalities, if you made or sold more than that, then you would start to incrementally make an actual net income of something, more and more values. But we're not solving inequalities, just equations. So where's the break-even point? Where does the cost equal the income? I want to be able to subtract them and get a value of 0. I don't want to lose money. Making money would be great. I'll just hopefully sell more widgets, but where's the break-even point? Where does cost equal the income? Well, by saying that, I'm actually telling us how to set up the problem. Where does the cost, 1,500 plus 1.45, and let's call it W for widgets, so when setting up word problems, it's always extremely important to define the variable. So we have 1,500 plus 1.45W is equal to 3W, 3 times the number of widgets. Okay, so now we have to solve, really, this is an easier problem than pretty much any of the ones we've solved for so far in this lesson. We need to look for parentheses, we need to combine like terms, none of that. We need to get the variables on each, on the same side of the equation. 145 is less than 3. I could subtract both sides by 3W if I like to just always keep my variable on the left-hand side of the equation. But if I do that, there's not going to be anything on the right. And as long as you write, say, like a equals 0, then you're going to be okay. A lot of students forget to do that, though, and they just sort of move the variable in between the two numbers. So I don't really encourage my students to move their terms around in their equation to get one side to equal just 0. Not that that's wrong, but then they sort of let the equal sign float around, and that's where they kind of run into some trouble. So we're going to subtract both sides by 145W, and we're going to get 1,500 is equal to, now let's see here, $3 times $1 is $2, $2 times 40 cents is going to be $1.60, and then $1.60 minus 5 is $1.55, or $1.55. Dollars kind of makes sense for this problem because that's what we're talking about is money. And we're going to now now that we got that subtraction done and we've moved our variable to the right-hand side of the equation, we need to move everything to the left. Well, we're only one step away. With our w, we have a multiplication of 1.55. So we're going to divide that 1.55 from both sides of the equation, and w is going to be equal to 1,500 divided by 1.55 is 967.7. Now, if I want to check that answer, I need to take that and plug it back into the original equation to make sure that the two sides are an exact match. Now, it'll be a solution, sorry for the static, it'll be a solution, assuming that that is a correct setup for this equation, but at least you can show that it's a solution for the equation you came up with. I'm going to pause though and just say this is a real-life application problems, if you will, and you can't make or sell, I'm assuming, 9.67 or 967.7 widgets. You need to make a whole number of widgets, and so if I want to at least break even, we need to say that W is equal to 968 widgets. That'll guarantee that we break even. Now, if you sell anything more than this, you're going to then start making a net income which is positive and actually create an income that is meaningful for your company. Got one more word problem. Bam! Bam! Last example. You travel to your parents' home averaging 60 miles an hour. Returning home, you average 50 miles an hour, and it takes you 2 more hours to get home. How far do you live from your parents, and what is the average rate of speed for the entire trip? Well, anything in motion, pretty much, especially in algebra, is going to be dealing with distance is equal to rate times time, or D equals RT. Distance equals rate times time. And you are traveling to your parents' home, from your house. So you're here at your home, you travel to your parents, you hang out, you come back, and so you're home, parents, back home. So the distance that you're traveling in each direction, assuming you have traveled the same, path, they're going to be equal. So how far do you live from home? You're going to take advantage of the fact that each of these distances are the same. So we have sort of like a D1 and D2, D sub 1 and D sub 2 here, if you will. But really, you don't even need to write them as with a different subscript because, again, they are the same length. So from home to your parents' house, your rate was 60 miles per hour. And I don't know what time is because I'm not given very much information about the time. But going this way is equal to 60 times t. And then when you head back, you go a little bit slower. So your rate is going to be 50. And now here you are being told something about the time it takes. Coming home, it's 2 more hours. Well, 2 more hours than what? It's 2 more hours than from your house to your parents. So I do not know the time that each of these trips take, but I do know something about the trip home. It was because you were going slower, whatever the time was to get to your parents, plus 2. It was 2 more than. It was 2 more hours to get home than it took to get there in the first place. Well, now I have an expression for the distance between home and your parents' house, 60t, and then getting home, 50, the rate, times time, t plus 2. And now we're just going to set these equations equal to each other, or these two expressions equal to each other, because they're both equal to the same value of d, the same distance between the two houses. So we've got 50 times t plus 2 is equal to 60t. Okay, we're going to look for parentheses that we can distribute through, and that means that we're going to distribute by the value of 50, and we get 50t plus 100, and I don't like the fact that my equal sign doesn't line up there. Sorry about that. 50 times 2 is 100 is equal to 60t, and I don't want to create any unnecessary negative coefficients. I don't really want to move terms around to leave just a value of 0 on one side of the equation, just because I see that mess up my students a little bit, and there's no reason why we can't be comfortable with having variables on the right-hand side of the equation. Just give yourself some practice. So we divide both sides by 50, and we're going to get 100 equals 10t. Now with the remaining variable, the almost isolated variable, now that we have it not on both sides of the equation but just one, we're going to undo that multiplication of 10 by the inverse math operation, which is division, and we get an answer which is that t is equal to 10. And we can assume that since we're talking about, oh, by the way, you might not understand this, mph is miles per hour, or miles over hours, and that means that our time period is 10 hours. Now, t was 10. Now, this is a word problem. It's applied to driving. Now, what the heck was t? T was the time it took you to go from home to your parents. So it was 10 hours to your parents' house, and it took you 2 more hours to get home. Well, that means that it was 12 hours to get home. Now, I'm taking some time to write some values out in terms of, or in context of, the actual problem, but I don't think I actually answer the question yet. How far do you live from your parents' home? Well, again, the distance from home to parents is either d, 60t, or parents to home is d is 50 times t plus 2. So really, I'm actually going to check my answer of time is equal to 10 to parents and 12 to get home. I'm actually going to check that in the way that I'm going to answer this question. How far do you live from your parents? Well, I live from my parents 60 times the number of hours to get there, which is 10. So that comes out to be 600 miles. And if I really want to make sure that this is right, after I get the phone. So again, if I want to make sure I'm absolutely correct, we said it was 12 hours to get home. So I can keep that value of t, which of course is 10, or, I have the 10 plus 2, which is where I got the 12, and 50 miles an hour times 12 hours, again, that is going to come out to be 600 miles. So I have not only answered the question, yes, in this particular problem, if this were the scenario, you live, let's see, 600 miles from your parents' house, but by doing it to both of these expressions and making sure I get the same answer, I've checked my answer. What is the average rate of speed for the entire trip? Well, if distance is equal to rate times time, and I have a question about what is the average rate of speed, get out of the way here, then I can take this equation of d is equal to rt, divide both sides by t, and this is a little preview of what we're going to be doing in our next algebra lesson, which is solving literal equations, which is an equation with more than one variable in it. We want to isolate this r for rate. We're going to do that by doing the inverse math operation of multiplication, which is division, and get distance over time is equal to rate. Now, if we're talking about an average rate of speed, that's the total distance over the total time. And the average rate of speed is not going to be an average of 50 and 60, because 50 plus 60 is 110, and 110 divided by 2 is 55 miles per hour. Our average is not going to be dead in the middle or dead center because of the time difference. We didn't drive 50 and 60 miles an hour for the same period of time, so we got to get that total distance over the total time. Well, if it's 600 miles to your parents' house and 600 miles back, that's a total distance of 1,200 miles. So our average rate is 1,200 over our total time for the average. Well, our time there was 10 and our time back was 12. So that's going to be 22. So we have 1,200 miles and a total of 22 hours. And we drove for 50 miles per hour longer, so the average should not be right in the middle at 55. It should actually be more towards the lower value of 50 because we drove that speed for a longer period of time. And 1,200 miles divided by 22 hours does come out to be 54.5 hours. And there was a lot of examples in this video. I hope that you got through them all and understood everything. This is the end of my lesson. I'm Mr. True. Bam! Go do your homework.